Okay, so we're talking about center of mass. Let me remind you what that is. That's the point on an object that is extended. It has a size or shape. It's the point that behaves the same as if all the mass were concentrated there. So it's basically your ambassador for all the point particle physics that we learned at the whole beginning of the class, back when objects didn't even have size and shape. So now, not all the points in the object will behave like we talked about before. Only this one point will, so it's important for us to be able to find it. So I talked about the balance method, which is a nice way of figuring out where is the center of mass for an asymmetric object that's basically the mass is all along a single dimension. Okay? So what you do, again, just to remind you, here we have an object which has some degree of asymmetry. Obviously, there's more mass on one end than the other. Now, we call the exact halfway point between the ends, we call that the midpoint, or sometimes to be fancy, the geometric center. So that's just halfway between my hands right now. But the idea of the balance method is that we try to find that point that this thing balances on my finger. It's right about here. And the idea is that if you can support an object with a single support force, you found the center of mass. Because if we'd have to take the pull of gravity on this object collectively to be somewhere, that somewhere is at the center of mass. So that's where we take the force of gravity on the object as a whole to pull. And if we don't want it to fall down, using a single support force, we need to hold it there. Okay? So I've managed to find the center of mass like that. And of course, I want to point out that this is not the geometric center. And this is probably the biggest conceptual takeaway for center of mass, is that center of mass is skewed towards the larger mass. If you have more mass toward one end of the object than the other, then the center of mass is pulled towards where there's more mass. So you can see here that it's significantly to one side of the midpoint. Okay? And I wanted to remind you of this, especially because the next method is just going to be the two-dimensional version of this. Okay? So the next method is called the hanging method. That's basically a two-dimensional equivalent. So let me show you how this works with some two-dimensional objects. Here's an example. So this object, it doesn't have much thickness, but it does have mass in both the x and y axes, right? Two-dimensional. So I'm going to hang it like this, and hang it again from a single point. And what you notice is it comes to us like this. And when it balances, it's because the single support force is directly above the center of mass. So it looks like this. So if you have some kind of weird shaped object, the center of mass, the support force has to be directly above. Because the force of gravity pulls at the center of mass. And so basically the center of mass is now just pulling downward against the pivot, so as long as I can hold it up, this thing will stay. So let's do this. I'll hang it like first using this hand here. I'll hang it. At first, it swings down until the center of mass is below the support. So the center of mass, I haven't narrowed it down. It's just somewhere along this line, right? So it's just somewhere underneath my fingers. I don't know exactly where, but you can do it from another point. And now the center of mass is somewhere underneath here. And of course, there's only one point that is underneath both suspension points. The center of mass is right there. If I do it from any other point, I'll just get corroborating evidence. Okay? So what you see is that in order to narrow down the center of mass for a two-dimensional object, you just have to hang it twice. Okay? From two different points. So basically, you hang it a couple different times, and the center of mass is narrowed down, like so. So that is the one point of that object that will behave as if all the mass were concentrated there. If I threw this object up in the air, that point would have to go straight up and straight down. The rest of the points could spin. I'm not going to do that because this thing has a lot of sharp corners, but I'll do a couple other objects and I'll show that to you. I can do that. Let's try this one. Where did I put my piece of chalk? There it is. Okay. So I'm going to take this kind of bizarrely shaped object. I'm going to hang it once. Center of mass is somewhere underneath here. Okay, hang it twice. Center of mass is somewhere underneath here. And if we find something interesting, the center of mass of this object is outside the object. The center of mass of an object does not have to actually be where there's any physical material. This is the center of mass of this. Now, a human being can also fold into this shape. If you reach down and touch your toes, you kind of look like this. It's possible for your own center of mass to be outside your body. Okay? You see this all the time with divers flying through the air like this. Okay? The center of mass is undergoing the classic arc-shaped trajectory, but the diver is actually spinning around it like this. Okay? It's subtle. The center of mass is not that far outside their body, but it can be outside the physical material. Now, if you don't believe me, a classic example is just a ring. Okay? So if you applied the hanging method to this, or just use symmetry, you could figure out the center of mass of a ring is right in the middle. And you'll probably agree it's the middle of the ring that's required to go up and down like that, even though no actual physical material of the ring does that, right? Let me show you another one. You can take this object right here. We can hang it once. Center of mass is somewhere underneath there. Hang it twice. Center of mass is, whoa, I'm not getting the right answer. Let me try to do it a little more carefully. So let me hang it once. Center of mass is underneath there. It's hard to do like this, drawing a vertical line. And then I'll do it again, hang it like this. No, I mean like this. And there seems to be something wrong with this disk. The center of mass is getting, this is the geometric center, it's getting pulled to one side. Now the reason why is because if you felt this, if you pick this up, you'd immediately sense there's something wrong with this. There is more mass on this side. So inside this thing, the mass distribution is not even. There is more mass toward this side. That's why, again, conceptual checkpoint, center of mass is skewed towards the larger mass end. Now this is an object that I can actually toss in the air, and you can watch what a strange trajectory it has, because the point that is going to go straight up and straight down is not in the center. It's going to look like it's wobbling. Right? Yes? You see a wobble? Okay, that is because the point that has to go straight up and straight down, the center of mass, is not actually in the physical exact midpoint of this disk. You can really have a lot of fun with this. You can, for instance, take this object. There's no glue involved here. Okay? The center of mass of this system is probably, this is a very, very lightweight plastic horse with a very heavy metal ball. The center of mass is probably somewhere here. And so this is just a funny looking pendulum. Okay? So the center of mass is here, and I'm supporting it directly from above. Okay? So just a weird looking pendulum. Here's another thing. I have this eagle. Okay, so I can balance this. Okay? And again, if you pick these things up, you'll very quickly notice that there's something very wrong with them. The mass is not distributed how you think it is. All of the mass is in the wingtips on this. There's a heavy metal weights in these wingtips. And so the center of mass is basically right here. Exactly between the wingtips, and the beak is designed to be directly above that. So basically this is a funny looking pendulum. I'm supporting the center of mass directly from above. Okay? You can try these things out if you want. So there are some examples of center of mass. The fourth and final method is going to be the one where we actually use to calculate. You have several problems on your homework that involve this. So are there any questions on this before we move forward? I need to clear a little space. Yeah?
Is there a name for objects that have the center of mass not inside of them or not on them?
I don't, not any lingo or nomenclature that I'm aware of. I mean, you know, you're lucky if you happen to get a symmetric object. Most objects are going to have some kind of at least slight mass asymmetry that is going to cause their center of mass to not be totally obvious. Any other questions? Okay. So let's calculate. Yes, this is method 4. It's the first calculational method. Let me show you how you do this. So let's say I have an object like this. I'll call this M1, I'll call this M2, and then I'll say that the connecting rod between them is low mass, massless. So that just keeps these two masses together as one object without adding any additional complication. So here's what we do. We first put down a number line. And then what we do is we identify what are the locations of both of the masses on this number line. So x1 and x2. So now we have quantitative information about what each mass is and where it's located. And that's the raw material we need to calculate the center of mass. So first let me tell you what you don't do. You do not want to do this, x1 plus x2 over 2. Now that would give you the x value of something, but it would just give you the x value of the geometric center, the midpoint. So this would be the geocenter. It would give you this location right here. But we know that the center of mass is not there. If you look at the picture, it's seeming to suggest that there's way more mass on the left end than on the right. So we need to acknowledge that, right? Let me give you some numbers here. Let's say, I want to get the same numbers as in my notes. Let's say 15 kilograms and 5 kilograms. So there's 3 times more mass on the left end as on the right end, right? So what do we do? Well, what we could do is put in x1, and let's put that in 15 times, right? It's kind of like playing the lotto, right? So you put in more tickets, okay? So we'll put x1 in 15 times because there's 15 kilograms there. And then we'll put in x2. We'll put that in only 5 times. So just like if somebody else has 3 more tickets in the lottery than you do, they're more likely to win, right? By the way, how many total values am I going to have here? 20, right? So I have to divide by 20, right, to get the average now. That would give me x comp. Now this is a strange way of putting it. Let me simplify what I just did. I put in x1 m1 times, right? I put in x2 m2 times. And the thing in the denominator, which is the total number of values, is just m1 plus m2. there is my formula for finding the center of mass. It's a weighted average, no pun intended, because what you're doing is you're going to weight each position by how much mass is there. X1 is more important because M1 is larger. Okay? You do this kind of thing all the time. Like, for instance, if you're trying to compute how you're doing in a class so far, right? If you got an A on a quiz and a C on an exam, right? Your class average isn't a B, isn't it? Right? Because the exam's worth more. So what you have to do is you go to the syllabus and you take the weights, right? You multiply every score you have by how much it weighs, how much it counts, right? And then you, of course, divide by the weights if you're going to only do a partial average, right? So if you're taking a 5% quiz and a 20% exam, the only maximum is 25%, right? Does that make sense? So that's what we do in the center of mass. We just count a mass more or we count a position more if there's more mass there. This, by the way, will gladly extend to however many you happen to have. In fact, let's go ahead and take it out for a spin. Now, I think it's fairly straightforward. So one of the things that I'd like to do, just to kind of make it so that I don't have to do too many examples, let me give the connecting mass, the connecting rod some mass. Let me see, that's 10 kilograms. So what might we do then? Well, that one is a bit tricky, of course, because it has mass in a bunch of different places, right? But let's say at least it's a uniform rod, okay? So if it's a uniform rod, then the rod itself, where can we take that mass? Exactly in the middle, right? So we're going to have an X3, and this is going to be my M3, and that's going to be exactly in the middle. And I guess the one other thing I need to make this a quantitative calculation is I need to give you the length of this thing. So this is going to be a 5-meter length overall. So it's 5 meters length of rod. Now, the other thing that so I'm going to find the center of mass of this, one of the things that I can do to make my life easier, I don't need to pick the origin out here randomly. I might as well pick the origin at some convenient location. So let me pick the x equals 0 here. This is entirely up to you. That's just going to make your life easier. So with that origin, what's my x1 value? 0. That's convenient. What is my x2 value? Plus 5 meters, right? What's my x3 value? Plus 2.5. So I trust that you can plug those in. Plug in the masses, plug in the x values, and let me tell you what you get. You will get x com is equal to, and make sure you can get this at home, the x com should come out to be plus 1.7 meters. So where would that be? Well, it'd be roughly about here, right? Does that make sense? Is that about the right spot? Should it be to the left of the midpoint? Yeah. It should be skewed towards the left because it is there's more mass on there. So that's the center of mass somewhere around there. Question?
Yeah, does that suggest that the center of mass is a vector because you put a plus?
Well, yeah, sort of in that it's a position, but it's just an x coordinate, right? It's a location. I mean, we talked about the fact that you can turn position into a vector. Here I'm just talking about the x coordinate. Yeah?
Where are you going to plug in x3?
You just extend this formula out, right? So m1 x1 plus m2 x2 plus m3 x3. And then here add m3 to the list. It's like if you're trying to compute your average of 3 scores instead of 2, right? So this formula extends out to however many things you have. So all you have to do is identify their locations, x1, x2, x3, x4, whatever, and then multiply each of them by how much mass is there, and then divide by all the mass in the bottom.
So x3 is not necessary to be in the middle between x1 and x2. You just create that number.
I just happen to label it x3 because I already labeled 1 and 2. So you can number them however you want. That's just your numbering scheme.
The location of x3 is just any other random number, but not necessary.
In general, it can be, but in this case, what I called the third mass was the rod, and the rod is if I have to take somewhere for that 10 kilograms to be, it's in the midpoint of the rod. Are there any other questions? Okay, so now this is all location relative to an origin. Okay. So maybe your friend chooses a different scheme. Let me show you. Maybe some people like to take x equals 0 at the middle. Okay. Is there anything wrong with that? No. Okay. Now, if you picked x equals 0 at the geometric center, then in that case, what would the x1 value be? Negative 2.5. What would be the x2 value? Plus 2.5. And x3 would be 0. And if they did that computation, they would find that xcom was negative 0.8 meters. Which means it's 0.8 meters to the left of their origin, which, by the way, is exactly the same place. So the center of mass isn't different. It's just what you're using as your reference is different. So don't get into a big fight over it, lose your friendship over it, and then 20 years later realize you were talking about the same location. Okay? Now the reason I say that is because you should never hesitate to choose whatever origin makes sense to you, but WebAssign can't read your mind. Which means that in WebAssign, it'll always ask, what is the location of the center of mass, and then it'll have some sentence fragment afterwards saying what reference it's talking from. So it might say, for instance, to the right of M1, or it might say to the left of the geometric center. They're different things. So don't feel like you have to use what WebAssign is suggesting, but you might need to tweak your answer slightly before you throw it in. So if you feel more comfortable finding it 1.7 meters from here, and you discover at the end that WebAssign wants it from there, just adjust, right? No problem. So remember, x equals 0 is in the eye of the beholder, right? There's no universal x equals 0 in Wichita, Kansas or something, okay? So it's up to you, but then you have to realize that your answer is relative to that personal choice. Are there any questions on that? Okay, and I should mention that this doesn't just work in one dimension, this does work in multiple dimensions as well. If you have one problem on your homework like that, where let's say you have these objects scattered out in two-dimensional space. So then you can go ahead and pick an origin, whatever you want. One choice you might make is like on top of one of the masses. So x1 and y1, of course, those are both 0, 0. You purposely chose that. And then, of course, you can also identify the x and y coordinates of both of these masses, right? That's x2, that's x3, this is y3, this is y2, okay? So what you do, to find the x-coordinate of the center of mass, you use the exact equation that we just used. And for the y-coordinate, you do the same thing but with the y-coordinates. So you take all the y-coordinates, multiply by how much is mass at each one, and divide by all the masses. So that formula and the old formula will produce a coordinate, x, y. So maybe it's somewhere about there or something like that. So you can find the coordinate in two-dimensional space of the center of mass. Any questions on that? Again, pick whatever origin you're comfortable with. In this case, I've chosen the origin such that all of my masses lie in the positive, or in the first quadrant, right? So I don't have to deal with negative x or negative y values. But there'd be nothing wrong with that either. So this is just going back to your math class. Can you put down an origin and identify coordinates? Okay. So that's it for center of mass as far as how to find it. The next order of business, which as I mentioned will span several homeworks, is to talk about the rest of the object in terms of rotation. So that's what we're going to move on to next. That is still on your homework number 8. So at this point, you should be able to do all the problems on homework 8 involving momentum, energy, and center of mass. And you'll find at the back half of the homework there is some stuff on angular kinematics, which is what we're doing next. So any questions before I clear off some space on the board and change gears completely? Okay, so let's talk about angular kinematics. So before I even start in on that, our next unit is going to be angular motion. This is going to span homework's back half of homework 8 through the front half of homework 10. That is actually going to, the exam number 2 cutoff is within there. This is going to be a fairly large unit, and I want to give you an overview of what we're going to do. What we're going to do is just introduce the bizarro version of everything we've talked about in the class so far. So what we've talked about so far is linear, also known as translational physics. We didn't call it that because, of course, we had nothing to confuse it with. But all the stuff we've been talking about so far is a point particle flying through space, translating through space, or moving linearly through space. Doesn't mean literally in a line, but it means moving in some path through space. That's in contrast to angular, also known as rotational physics. Interchangeable words, you'll hear them both. So let's go back and look at what we've done and what we're going to do. We introduced displacement, velocity, and acceleration, right? These were just the descriptors of motion, okay? So just how can we describe how things move? We even had a nice toolkit for a specific type of motion called constant acceleration. These were called the constant acceleration equations because they describe one particular type of motion. It's not the most complicated type of motion possible, but it's the most complicated type of motion we look at. So things are changing their velocity, but they're changing their velocity in a smooth manner, okay? So this was the kinematics. This, of course, was your homeworks. I think we started homework 1, and really this was homeworks 1 through 3, although, of course, we continue to use these later on. They weren't the primary focus. So first we did it in 1 dimension, then we did it in 2 dimensions, right? Which required all the vector components and stuff like that. Now we can do all the same stuff in the rotational world. Going along with displacement, velocity, and angular and acceleration, we have all their angular counterparts. Angular displacement, angular velocity, angular acceleration. And again, don't worry so much about writing down what those things are. I'll go through all of them individually, and they're exactly analogous to the other list. This is the Greek letter theta, the Greek letter omega, which looks like a rounded off W, and a Greek letter alpha. We often use Greek letters for this stuff. You might ask, is there an equivalent set of equations? Yes. Constant angular acceleration equations. In fact, this is angular kinematics. Angular kinematics, that is going to be the later part of your homework number 8. So, let's walk through what we did before. After we were really good at describing motion, we started to ask why. Why do things move the way they do? And that's where Newton's laws came in, right? So, we learned that the net force on an object was what determined how it accelerated, right? And in fact, the third ingredient was mass. So these two are combined into F net equals ma. And that, of course, is our link through to kinematics. So we are able to now calculate the acceleration of things ourselves, as long as we know the net force on an object and we know its mass. And we can tie that in. We were doing that in homeworks 4, 5, and 6. There was still some mention of calculating displacements and times and things like that. You might ask, is there an angular counterpart to both of these? Yes, there is. What's the angular version of force? It's called torque. You may have heard of torque. We use the Greek letter tau. It's a T with a warped top. There is even an angular version of mass. How stubborn something is to changes in the rotational world. It's called rotational inertia. So instead of just inertia or mass, it's rotational inertia, I. You might ask, is there an equivalent to Newton's second law? Yes, there is. The net torque on an object will cause it to angularly accelerate, and how much or how little it does is dependent on its rotational inertia. So, whoosh, we go up here, and we have the same exact time. So, remember I said everything is going to be the bizarro version of what we've already talked about. This stuff, by the way, will be on homework 9. Homework number 9 will be the last homework that is on your second exam. But that will not be the end of the analogies. Now, once we were done with the forces stuff, which was homeworks 4 through 6, what was the next unit we talked about? The next major area. Yeah.
Energy.
Energy. That's right. So, you might ask, what about energy? You can have, we had something called energy of motion, kinetic energy. Another way you can have energy in your motion is if an extended object is spinning. You can have something called rotational kinetic energy. So there's two ways that something can have energy in its motion. Either it's because it's flying through space or it's rotating upon itself. This was on your homeworks number 7, and of course a little bit on homework 8. But homework 7 was the big energy homework, right? And then, what was the next topic we talked about after energy? What is it? Well, work and energy was the one big unit. Power was work per time, so still a big energy unit. Momentum, that's right. So this was a completely different way of analyzing a system, thinking about forces internal versus external, right? You may ask, is there such a thing as angular momentum? Yes, there is. We use L for that. This stuff is on your homework number 10, which will be on your final exam. What was the next thing we talked about after momentum? This is going back to last lecture. Center of mass. I'm going to put that right here. Center of mass is kind of like what bridges the gap. And the reason I say that is because the center of mass is the ambassador for all of the old stuff, right? It's the one point that's guaranteed to behave according to all of our old physics, but it also often forms the pivot for rotation for the rest of it, the rest of the object. So center of mass kind of like is the glue between them. The center of mass is obligated to obey old physics. The center of mass is often the pivot for the new physics. That right there, in a nutshell, is homeworks 1 through 10 of the course. I guess while I'm at it, I might as well put the whole course down. We'll do a unit on simple harmonic motion. We'll do fluids. So that simple harmonic motion is the second half of homework 10. Fluids is homework 11. And waves is homework 12. And then that's it. So right now, the entirety of the course is on the board. Obviously, there's a lot of detail on how to do things, just kind of the workmanlike aspect of tackling things, but the entirety of the course is on the board at the moment. Question?
So basically, you taught us like forces and all in the beginning of the year in order to set up for us when we do angular rotational physics.
That's right. We're going to do what it took us 8 homeworks to do before is going to take us 3 homeworks to do now, because it's so similar that we just have to learn the subtle differences, but other than that, all of the things that you have learned before you can draw upon. So the idea being that I'll kind of point out how it's different, but it's not that different. Okay. Are there any other questions? Okay, so that's kind of a survey of where we've been, where we're going in the near future, and just a general overview of the whole thing. And by the way, this is all called usually mechanics. So this is basically a course in mechanics. So electricity and magnetism and light and stuff like that, that's what Physics 2 is about, for those of you that have to take Physics 220. All right, so let's go on here and start into angular kinematics. Angular kinematics. Let's start from the top. Let's first talk about angular displacement. So, the underlying assumption here is we're moving in a circle. So that's already taken for granted. So let's say, for instance, we move from point A to point B. By definition, if you move between 2 points on a circle, you're covering some amount of angle, right? So this might be delta theta. Only 2 things you really need to know about this. We want to generally do this in terms of pi, okay? So rate pi, talking about angles in terms of pi, is going to be the SI unit. I mentioned at the very first day of class that we'll use degrees for a while until we get really serious about rotation. Then we have to remember we should probably use pi, and that time is now. So in terms of pi, so that's called radians, and usually not in degrees. And you'll see why that's really important in just a moment. So you guys hopefully know that a full circle is how much? 2 pi, right? Half circle's pi. Right? 90 degrees is pi over 2. Things like this? Okay, good. So 1 revolution is 360 degrees, is 2 pi radians. Those are all different ways to describe a full circle, but we are going to prefer radians. Radians is going to be our SI unit. The other thing that you need to know about angular displacement is that the sign convention we use is very much similar to one dimension. So remember in one dimension, when we had one-dimensional motion, we set a positive axis like plus x. And we said that things that point that way are plus and things that point that way are minus. Well, two-dimensional circular motion is very much the same thing. Now you might say, well, aren't you moving in 2 dimensions? Yes, but it's a highly restricted 2 dimensions. You can either go one way or the other way, right? You can either go counterclockwise or clockwise, and that's it. So there's only 2 ways you can move. So let's use plus for one and minus for the other. So we'll say that if you're moving in the counterclockwise fashion, that's plus. And if you're moving in the other way, where to put that? Let me just put it on the side. So counterclockwise is going to be our plus, clockwise is going to be our minus. Now you might question why we would do that, because don't we watch clocks all day, right? Isn't that the forward progress of time? Doesn't a clock move clockwise? Yes. So why do we pick that to be negative? Well, in math class you probably know that counterclockwise is more intuitive, right? So in math class, for instance, when you have an xy axis, how are the quadrants numbered? 1, 2, 3, 4, right? This way. So we take counterclockwise to be plus, we take clockwise to be minus. So for instance, in this case, since I said you go from A to B, this would be a positive angular displacement. Okay? So you just put how much angle you traveled, and you put a plus or minus depending on whether you went clockwise or counterclockwise. Okay? And when you say how much angle, put it in terms of pi. I should mention that if you go like this, and you close your circle, we wouldn't call that 0 displacement. We would call that positive 2 pi. Okay? If you traveled in a single direction, then it'd be weird if the displacement was 0. Think of it as like one dimension, right? If you travel in a single direction, you can't ever get a displacement of 0. And we want those same rules to apply even though we're looping the same circle over and over again, right? So for us, whoops, vector hat there, it doesn't count if you go all the way around a circle and come back to the same point. We don't call the displacement 0. If you do 1 lap, it's 2 pi. If you do 2 laps, it's 4 pi, right? Displacement doesn't have to be 0. The only way the displacement can be 0 is if you went one way and then you came back. So we might call that displacement of 0. That's different. Just like we would in one dimension, right? You go one way, you come back, we call that 0 displacement. So basically we have to ignore the fact that a circle continuously loops on itself, right? So we don't get credit, we don't get 0 displacement because we happen to loop around once. That's 2 pi. Question?
So wouldn't the point be like, when we come back around, wouldn't the point be like off center from the 0? Like say, this is like 2 pi right here and 4 pi right here?
Yeah, well, but I mean, you could literally come back exactly through the same point, right? Like, for instance, if you're running around the track, right, you can run through the exact same point, but we wouldn't call it a 0 angular displacement. So let's talk about how this, now this is a completely new way of thinking about what you do going on a circle, just talking about angle covered. But you can relate that back to stuff we were talking about before. You're of course still covering distance, right? Yes, you're covering angle, but you've also covered a distance s. So we can relate the distance you've traveled to the angle you've covered. That's with the arc length formula. Do you guys know that from math class? Right, so S is equal to what times theta? R? Have you guys seen this before? This arc length formula?
Oh, yeah.
Sort of. If you haven't seen that general case, you definitely have seen the special case of it. What do we call it when the distance, not just a segment of a circle, but what do we call the distance all the way around? Circumference. And how much angle is around once fully? 2 pi. Have you ever seen this formula? Circumference is 2 pi r. Right, that's just a special case of the arc length formula when you happen to be doing a full circle, right? The formula works for any fraction thereof. Okay? But let me point out that it does not work if you don't put in the angle in pi. Circumference is not 360r. It doesn't work if you put it in revolutions. One circle is 1 revolution. Circumference is not equal to radius. Those don't work. You see why you have to go into pi, right? You have to talk about angles in terms of pi for this relationship to work. Okay? Now let me point out that S is in terms of meters, that's a distance, and R is also in terms of meters. So that means that this really has to be unitless. Radians is really a way of describing angle without units. For instance, if I take this and I solve it for pi, pi equals circumference over 2r, or as we call 2 times the radius, sometimes we call it the diameter. So measuring angles in terms of pi is basically measuring a way of ratios of distance around to distance across a circle. And every circle has this strange property that the ratio of the distance around to the distance across is a number called pi that never repeats and never ends. 3.1415926535889, so on and so forth. Okay? They have contests where they memorize this for 8 hours and recite it to 100,000 digits. Okay? It's pure memorization. There's no pattern. It's a transcendental number. Okay? It's surprising that something that crazy would come out of something so simple. But it is a way of measuring ratios. So when we measure angles in terms of radians, we're measuring ratios of distances around to distances of the radius. Okay, so we'll pick this up next time.